Now in this video, we're going to do really the same thing we did in the last video, but for some special angles. So in the last video, our angle lengths, or I should say our angle values, weren't actually known. We just called them theta. Here we're going to look at them for very specific thetas. So for the first one we're going to do is 45 degrees or pi over 4 if we're in radians. And again, I'm going to let this be my 45-degree angle here. So I'm just going to label this as my theta and be specific that this is actually 45 degrees. Now, something to think about here. If I have a right triangle, this angle is 90, right? And in case you've forgotten, the sum of all angles in a triangle is 180 degrees. So in this one here, we know is 90 degrees, and this one we've just said is 45 degrees. So 90 degrees plus 45 degrees is 135 degrees. And if I take 180 and I subtract it with 135, I get my missing angle. And we see that this other angle then must also be 45 degrees. It just works out mathematically, has to add to 180. So the other angle would also have to be 45 degrees. Now, if these angles are the same, then the legs on the other sides have to also be the same length. I can't have different angles in different leg sizes within the same right triangle for this 45 degree. It doesn't make sense, doesn't work mathematically. So you actually have, in this case, an isosceles triangle where two sides are equal. And also two angles are equal, so it's the same thing. So the thing that's interesting with this type of mathematics with the triangle is that the ratios really all work out. So as long as my two lengths here are the same, then my math will work out. So I'm going to let each of these lengths be 1 and kind of think of it as a unit circle idea. But I could also let each of these sides be 2 or 3. And when I simplify my math, I get the same answer in the end. So you will see sometimes that the sizes of the triangles could look bigger, or you could use different lengths. But if the angle is the same, it's not going to matter. It's all going to come down to the same ratio in the end when you do your sine, cosine, tangent, and so on. So I'm going to use 1 and 1 here, but if you tried it with 2 and 2, you'll see that you get the same result. So it's really about the angle and making sure everything works there. So I'm going to let these each be 1. And then I can find the other side by using a squared plus b squared equals c squared. So 1 squared plus 1 squared is obviously 1 plus 1 is 2. So 2 squared. And then I take the square root of both sides, and I get my c value here is the square root of 2. And there's nothing I can really simplify there. So our sine of 45 degrees then, or your sine of pi over 4, whatever units you're using, is still going to be opposite over hypotenuse. So my opposite is 1. My hypotenuse is square root of 2. And again, I'm going to clean this up a little bit. Actually, let's do that first. So I'm going to multiply by square root of 2 over square root of 2, which ends up giving me root 2 over 2. Now, when I do the adjacent over hypotenuse, right, I'm looking at this number 1 here. I get the same result, which makes sense because the two legs are the same. So once you clean this up again, you also get root 2 over 2. So tangent is opposite over adjacent. So my opposite is 1, my adjacent is 1. So I just get 1. Now, hopefully these values all look familiar to you because we've seen them before, and you can just see how they are consistent with the unit circle results. For cosecant, I'm just going to go ahead and take the reciprocal for sine. So I'm going to go ahead and it's going to be hypotenuse over opposite. So the hypotenuse is root 2. The opposite is 1. I just get root 2. You can also do it by flipping this one here, but then you'll have to clean up the denominator. So I just decided to go back to the original values instead. So for secant of 45 degrees, you're looking at hypotenuse over adjacent. So we're going to get root 2 over 1, again, which is also root 2 here. And then finally, cotangent of 45 degrees is going to be adjacent over opposite. Both of those are 1, and 1 over 1 is 1. So we're able to find all those values. And again, it still works here. So it's fine. As a little side note, again, just to kind of show you guys, I know I chose 1 as my length. If I chose 2 instead, and these are both 45 degrees, so they would have to have the same sides, then what happens is I'd have 2 squared plus 2 squared equals c squared. So 4 plus 4 is 8. So my c value would be 8, or square root of 8, or 2 root 2, if I simplify that. And if you start trying these values, for instance, sine of, I'm going to make this one my theta again, this angle here, 45 degrees is going to be opposite over hypotenuse. So my opposite is 2. My hypotenuse is 2 root 2. I rationalize that denominator. I have 2 root 2 over 2 times 2. And I get square root of 2 over 2. And you can see it was the same value I got when using 1 and 1. So as I was saying, you may see different size triangles with different lengths, but if the angles are the same, the sine, cosine, tangent, cotangent, cosecant, and secant are all going to be the same. It's about the angle. And that's because really we're doing ratios here. So as a triangle gets bigger, has longer lengths or shorter lengths, it's still staying in the same proportion if the angles are the same. So it's not going to matter. So, if my legs are 100 each, it's still going to be the same root 2 over 2 when I find sine of 45 degrees. I also want to do the angles of 30 and 60. So we did 45 degrees in the last one. So what happened where your angles were 45, 45, 90. When you have 30 degrees or 60 degrees, what happens is 30 and 60 always go together in a right triangle, right? They have to add up to 180. So if one of the angles is 90, you have 90 degrees left over, and 30 and 60 are how you get 90. So you get your 30, 60, 90 triangle here. So this one they kind of construct a little bit differently. So we start here with a equilateral triangle. So what happens is all sides are 60, or all angles, excuse me, are 60. So something like this is equilateral. Equilateral. So all sides are equal, which means all angles are also equal. And then what they do to get the 30 degrees and to make it a right triangle is they cut it right down the center. So I'm able to form a 90-degree angle here. And if I cut this in half, then what happens is each of these becomes 30 degrees. Okay. Now, again, you can really start with any lengths you want. I'm going to follow along with the most common examples here. And what happens is because you have a 60, 60, 60 original triangle, you have that in black, all sides are the same. So again, it doesn't really matter what you pick for lengths. All the ratios are going to be the same. It's pretty common to choose 2. So each of these full length sides would be 2. And then what happens is because you're cutting it perfectly in half, this part then becomes your side of 1. So I'm just going to kind of pull out that part of the triangle, because that's going to be our focus. Make it a little easier to see. So you have 60 degrees here. You have 30 degrees here. This is side 2, and this is length 1. Now, the only thing you don't have is you don't have this length here. So you will have to find that length, and we can find that using the Pythagorean theorem. Now, this is my hypotenuse right across from the 90 degrees. So this is my C. We can call this B, and let's say this one is A. So A squared plus 1 squared equals 2 squared. Subtract that 1 from both sides, and I have A squared equals 3. And I take the square root, and I have square root of 3 here for my side. So that's our initial setup. We're not done yet, but that's how they usually set up that 30, 60, 90 triangle. And again, you don't have to use 2s here. I could have used 3, 3, 3, 4, 4, 4. It really doesn't matter, as long as I have something that is equilateral, because we're starting with 60 degrees in each angle. So all the sides would have to be the same, no matter how big or small that triangle is. And again, it works out because if you look at all of our formulas, everything is a ratio. So it always keeps everything in proportion to one another. So let's go ahead and we'll do the 60 first. So I'm going to focus on, we'll use 2 different colors here. All right, so I'm going to start with red. So I'm going to do the 60 in red, just to kind of focus there. So sine of 60 degrees, which would be pi over 3. So I won't write them both out each time, but 60 degrees would be pi over 3 in radians. Again, is opposite over hypotenuse. So here's the angle I'm focusing on. The opposite of that would be here. So root 3. My hypotenuse is 2. For cosine of 60 degrees, you're doing adjacent over hypotenuse. So again, here's my 60. The adjacent is 1. The hypotenuse is 2. For my tangent, I'm doing opposite over adjacent. So opposite is root 3. Adjacent is 1. So I just have 3. So I guess I'm being specific here, 60 degrees. Hypotenuse over opposite. My hypotenuse is 2. My opposite is root 3. You do have a little bit of rationalizing to do there. So I have 2 root 3 over 3. My secant would be hypotenuse over adjacent. So 2 over 1, which is 2. And then finally, my cotangent, adjacent over opposite. So let's see, my adjacent is 1 and my opposite is root 3. And root 3 over 3. Now let's also do the 30. So I'm gonna be a little bit careful here because my 30 angle is this one. So my opposite and my adjacents will be different. So I'm doing sine of 30 degrees. Which is pi over 6. And again, I won't write it in both ways each time. You get the idea. And again, we're doing opposite over hypotenuse. So be careful here. This is my 30 degrees. My opposite angle is 1 now. So 1 over 2. Okay, so now I'm doing adjacent. So now my adjacent angle is the root 3, and my hypotenuse is 2. So you can see you have to really be focused on where is your angle, because the opposite and the adjacent can change. Okay, so for my tangent, opposite is 1, adjacent is root 3. Again, you'll have a little bit of rationalizing to do here, and you get root 3 over 3. For my cosecant, my hypotenuse is still 2. My opposite is 1, so this becomes 2. For my secant, my hypotenuse is 2, but my adjacent is this one here. It's the root 3. So 2 root 3 over 3. And finally, my cotangent, adjacent over opposite. So my adjacent in this case is root 3. My opposite is 1. Okay, so again, just being a little bit careful about which angle you're focusing on. I think writing in color helps, or like highlighting. I know I make mistakes all the time, particularly when I'm trying to look in a textbook and I see a little tiny picture and I'm just kind of going back and forth to my paper and the picture, my paper and the picture. I make mistakes so often. So it can help really to redraw that picture on your paper as you're working. Use color if you need to. So highlight which angle are you focusing on so that you can figure out the opposite and the adjacent. And you can even label those too. So whatever helps so that you don't make mistakes, because I know even myself, I make them all the time doing these formulas when I'm not copying the picture over. I'm just trying to look at it on a screen or on the book. I always make mistakes. So I always recommend copying the picture over first as you're working. And again, using color, highlighting which angle am I focusing on here, because it really does make a difference.